Good afternoon. So, welcome to the third of the Hydro-Geological Engineering workshop. Today's speaker is Priyanka Bian, and I request Mrs. Chaya to introduce about the speaker.
Now, is it clear? Am I audible to you? Hello.
Chaya? Yes, Chaya.
Yeah. Okay. Thank you. She completed her BE in Civil Engineering from BMS College of Engineering and procured her master's in the stream of Water Resource Engineering and Management from NITK Surathkal and received her doctorate from ISC Bangalore. She has worked as research associate at ISC Bangalore and worked effectively on investigating the groundwater consumption, coordinating with Bangalore Water Supply and Sewage Board, and many other. She has worked as project manager from Intelligent Water Supply Network Monitoring and Control for Equitable Distribution of Water at ISC Bangalore. She has also worked as assistant professor in the Department of Civil Engineering at MSRIT Bangalore. She has many publications and conferences under her name. Currently, Dr. Priyanka BL is working as assistant professor, Department of Civil Engineering, Geetham School of Technology, Bangalore. With this brief introduction, I would like to welcome Dr. Priyanka BN on behalf of Civil Department of JNC Shimoga for this workshop. Welcome, Priyanka.
Thank you, Ms. Chaya.
Yeah, okay. You can share your slide and you can proceed, Priyanka.
I'll share the slides. Hope, good afternoon, Manna. Hope my voice is audible.
Yes, Priyanka.
Okay, as Chaya introduced, I complete my PhD from Indian Institute of Science. So I joined Geetham School of Technology recently in August. So I have been working on the groundwater hydrology during my masters, also during my PhD. So and also had a brief a research experience in water distribution networks. That is kind of postdoc at ISC. Now I'll be concentrating more on groundwater hydrology. So groundwater hydrology is a vast topic. So I'll be specifically talking about or discussing about the parameter estimation, few case studies which I have done during my research. So, as you guys are aware about the groundwater. So the water which is beneath the ground surface can be termed as ground. Yes. So yes. So it can be in unsaturated zone as well as in saturated zone. And you guys are aware that unsaturated zone can be classified as three types. Where the first category is water zone, where the this extends up to the major root surface, and the next is the intermediate water zone, and next is the capillary water zone. And now I'll be concentrating on this saturated zone. So in this saturated zone, you have two types of aquifers, that is confined and unconfined. So in case of unconfined, you guys know that it is at the atmospheric pressure and the top surface is water table. In case of confined, there is a confining bed above as well as below. So that is called as the confining. aquifer. There can be a leaky aquifer also, and artesian and perched aquifers, as you guys must be aware of. So now I will be discussing about the parameter estimation. Why this parameter estimation is important. So we know that if you have done the literature review on groundwater flow, substantial research effort have been done on understanding the groundwater flow in the regional scale. So, but these studies have simplified the groundwater flow modeling, have neglected the anisotropy and heterogeneity, and also layering on the aquifer topography. So the main reason for this is incomplete knowledge of the hydrogeological information. So before knowing this topic, let me have a brief introduction to anisotropy and heterogeneity. So we hope this you guys know the homogeneous medium where the property is same throughout the spatial, and isotropic is in the direction. So heterogeneous means it is changing in space, and anisotropic even in the direction. So, and the layering needs to be considered because the thickness of each layer, the geology under the ground varies. So this is important considering any water models when you're doing for a regional scale. So, as I've already told, this simplification is based because of the incomplete knowledge. So, classified this estimation of aquifer parameters, we can do it by field experiments or by mathematical models. In field experiments, we all know that pumping test, search test, vertical electrical sounding, that is one-dimensional resistivity test, hydraulic tomography, all these things have been used. But, and coming to the mathematical models, there can be deterministic models, that is the numerical models, and geostatistical models where the statistics are used to estimate these parameters. So I have worked on all these methods, that is field experiment, analyzing the field experiment, as well as both deterministic as well as geostatic. So I'll be presenting a case study on these. First, I'll begin with the field experiment. So analyzing the field experiments, as we know that these tests, for example, pumping test, we consider what to be homogeneous, and we'll be getting only one data, that is K value or the hydraulic conductivity value is 1. So this is the first topic where I'll be estimating the anisotropic hydraulic conductivity, and the case study was done on the coastal aquifer of Karnataka. Here we have used one-dimensional resistivity data and combined with the two-dimensional electrical resistivity tomography, that is ERT, estimate the anisotropic in all the three directions. As we know that hydraulic conductivity is a tensor, and we have considered the major principal axis only to estimate the anisotropic. And in this case study, we have taken the Mukha aquifer, that is in the coastal Karnataka, in the Dakshina Karnataka region. So this is the location of the study area. As you can see, we selected this area as we had a lot of field experiments already done. That is vertical electrical sounding, ES, was done. ERT was, there are 12 ERT profiles done. Borehole logging data was there. A pumping test was done. So we had extensive field data. So we had selected this. So we have proposed a new methodology where we'll be able to estimate the hydraulic conductivity from the resistivity. So usually for the one-dimensional electrical resistivity, the thing is Archie's equation is used. So the Archie's equation connects porosity with the fluid resistivity as well as bulk resistivity. But they miss out the presence, they do not consider the presence of clay surface, clay materials or the clay materials in the aquifer. So Waxman and Smith in 1968 came up with a new equation instead of Archie's to estimate the porosity, where they have considered uh, this is K cation exchange capacity, this is BQ. So this term was added in, to the Archie's equation. So, but many researchers avoid this equation because there is a difficulty to estimate this, the BQ term. So the M is the cementation factor. It varies based on the lithology. A is nothing but the coefficient of torcity. So BQ is a term which cannot be estimated so easily. So many of the researchers avoided this Waxman-Smith equation. But what we have done here is we have used, we have simplified this equation, that is Waxman-Smith equation, in form of the equation which is shown in this. So we have simplified it, and this equation is in the form of a straight line. You can see y is equals to mx plus c. So this is in the form of a straight line, and if we know the resistivity of water, we can get the resistivity of the water, and we can get the information of formation factor. Formation factor is nothing but resistivity of water by resistivity of bulk resistivity of aquifer. So by using this, we can estimate the slope as well as the intercept. So this is the methodology which we have proposed. The data required for us, this is the one-dimensional resistivity data of the aquifer that can be taken from the VES data. The same wells or the wells where we have done the VES, we have estimated the fluid conductivity or fluid resistivity over systemics. And to clear, I have not been part of this field experiments. I have been majorly working on the analyzing the data. So by using this straight line equation, we have plotted, that is y and x is the fluid resistivity. Here we got to know that there is a two slope. Two slope. Positive slope indicates the presence of clay. So the BQ term we got as 0.0036. So which indicates there is a presence of clay and there is a cation exchange capacity in this. So this needs to be considered when we are estimating the parameters. So the next, also we found that there are a few geological formations like consolidated rocks. So where there is no clay formation. In case of unconsolidated formation, there may be clay present in it. So in case of consolidated, there is no clay. That is what we understood. There are two geological formations. So we use this estimated the intercept and slope. By this, we got the BQ value, which was used in Waxman-Smith equation to get the porosity. And from the porosity, we estimated the hydraulic conductivity by Cauchy-Kármán equation. And the next is about we have established the correlation. There were around 12 wells. So for all the 12 wells, we have done the correlation. This is the correlation. So we have got two correlations. As I've already told, there is positive slope as well as negative slope. Similarly, we have got two correlations, that is positive correlation as well as negative correlation. In literature, if you can see, many people have done this correlation. They have few literature suggests there is a positive correlation between the resistivity and hydraulic conductivity, and few suggest negative. So in this research, we have identified it can be because of clay. There is a negative correlation, and positive correlation is because of clay, and negative correlation is because of low or no clay content in the geological formation. So by using this K value. We know the resistivity value, we can estimate the K value, which we have already done. Now we have to validate whether the estimated K values is correct or not. So we have validated with the pumping test data. These are the wells which has both VS as well as pumping test. You can see the plus sign is pumping test wells and the circle is by VS. So these are the locations which add both. So at these locations, we estimate, we saw that the goodness of fit was good and it was 0.9. We thought this is a very less number of points fitting the validation. So we had extended the area that is from River Pavanji to Gurupura River, and we have taken few wells where we got around 20 wells, consisting of pumping test as well as VS. So even for an extended area, there showed a good correlation. So now we have estimated the hydraulic conductivity only in one direction or one way. So one at a point based on the resistivity. So what we did is based on this, can we use it for the ERT profiles to estimate in X direction as well as Y direction. So as the ERT profiles was done in X direction as well as in Y direction, that is in longitudinal and transverse sections. So we had to compare whether one-dimensional data can be used for the 2D. So this is the comparison. So whether 1D can be used. So this is VES was done near one of the ERT, and you can see that it closely matches, where you can see the top surface is showing the resistivity of say 650 and above, and here also similarly it was seen same way. If you go in depth wise also, the resistivity profiles were matching, and this is with the BS data and also the borehole logging data. Even borehole logging is a one-dimensional resistivity test, so we have compared that. So as this ERT profile was passing three of the borehole loggings, so we have compared, and this is the profile where you can clearly see it is almost matching with this ERT profile. The borehole logging data is matching with the ERT profile. So we thought we can use this one-dimensional estimated hydraulic conductivity for estimating the two-dimensional K values. So what we did, the ERT profiles which are along the coast were taken as YY, and the ERT profiles which was perpendicular as taken as KXX. So the KXX from the equation, the two equations which we have got, we have calculated the K. This is the ERT profile. Equivalent K is shown in this figure. Similarly, there are 12 ERT profiles, 6 in X direction, 6 in Y direction. So we have estimated 6 K profiles, and the K values were found to vary from 0.46 to 50 meter per day approximately. So which indicates the least K values indicates the presence of clay. And the next is about the KYY. This is about the KYY. Now we have estimated in KXX and KYY. Now to estimate in Z direction, that is vertical direction, what we have done is we know that there is anisotropic ratio, that is the ratio of KH by KV. So to estimate equivalent KH and KV, what we have done, we have considered these profiles. You can clearly see from this figure, there is a layering of clay in this particular figure. This means the depth can be estimated, and we know the K value to estimate KH and KV, equivalent KH and KV. So similarly, we have calculated for all the profiles, all the ERT profiles, the equivalent KH and equivalent KB by measuring the depth. When the depth is changing, if you can see. So based on the depth, this DI will change accordingly. And we have estimated the anisotropic ratio in all the profiles. And after estimating it, we have estimated the KZ. So the anisotropic ratio is almost 0.2 times the horizontal hydraulic conductivity in this particular region. So this was the main outcome where we have got this equation for the KZZ. So the main disadvantage of this particular field studies is one, it is local scale. You will be doing at a location. So you can't do it for all the location, and it becomes expensive, as well as it's not feasible to do when you're doing for a regional scale or a large scale. So we used geostatistic tool where we'll be upscaling the information which we have got at the local scale to a regional scale. So this is the next work where I've used geostatistical tool to estimate for coastal aquifer the K values. So the main objective of this paper is to generate layer-wise, spatially correlated anisotropic hydraulic conductivity. So in intrinsic upscaling, so we don't not consider the boundary condition and the domain size of the area or the aquifer. And in geostatistics, the main important point is the hydraulic conductivity or the parameter which is you are trying to estimate is considered to be in a random space. It is a random space function. So it can change in a random place, random way. So, and also the aquifer is considered to be statistically homogeneous. Statistically homogeneous means the mean variance and the correlation length will not change when you are upscaling from the local to the regional scale. That is assumed in case of intrinsic upscaling. So how the heterogeneity is mainly because of the correlation length. So correlation length is nothing but what is the length between one K value to the other K value. The change of K values from one to other can be estimated by correlation length. So as we know that hydraulic conductivity is a can be distributed normally, and we can consider log normal distribution as the K values can't go negative. So this is the we have used the variograms to find out the nils, range, and sill. So this can be used as the input for the intrinsic upscaling. So from the K values which we have estimated at ERT profiles have been used to estimate the mean, that is the spatial moments, mean variance, as well as the correlation, which is tabulated in the next. So yeah, we have from the ERT profiles, which is along the X direction, we have estimated the mean in each layer and variance. By this, we have also got the correlation length by the variogram. By fitting the variogram, we have got correlation length. Now, similarly, along the y-axis, as we have already estimated that in z-axis is from the anisotropic ratio, it is 0.2 times the horizontal hydraulic conductivity. So we haven't considered the here. So this is the upscaled hydraulic conductivity which we have got. And yes, in x direction as well as y direction. So this is the one method of upscaling. Now, As I've told, we have analyzed the field experiments data, and we have also used the geostatistical tool to do it. So the next method which we used is the deterministic way, that is by inverse modeling. So you guys have known about the calibration of the models. It is nothing but the inverse modeling, where you will be giving the state parameters and estimating the her parameters. So that is the deterministic way which we have followed. So same thing which is published in Journal of Hydrology. Here we are using the inverse modeling. So this is the gowning equation. So in inverse modeling, we have deterministic way. It is a numerical model. So the numerical model which we are solving, this partial differential groundwater flow equation, can be solved by numerical methods. So it can also be solved by analytical methods, but analytical methods for three-dimensional is difficult. So we can go for the numerical models. So numerical models, there is numerical method, finite element method is there, finite difference, finite volume method is there. So there are also few built-in models, such as ModFlow, which is already developed by USGS. So it is based on the it is based on finite difference method. FeeFlow, which is based on finite element. Sutra is from finite element, and PowerFlow is a combination of finite difference as well as finite volume. So in this study, we have used, this is about the models. What are the inputs when you're doing this three-dimensional modeling? So when you're developing a conceptual model, you have to know the initial conditions of the state variables and boundary conditions. What are the source to the aquifer and aquifer topography, and also flow, as well as I was doing the coastal aquifer, consider the transport parameters, the flow parameters when you're doing the regional groundwater flow, concentrating on flow, and the sink, that is what is draft from the groundwater. These are the main inputs for developing a numerical model or a conceptual model. So for the same study area, we have done the numerical modeling. So there are around 14 observation wells. From these observation wells, we'll get the hydraulic head. So when we know the hydraulic head, we can give input. We know the time, we'll be estimating the K in this. So we know what is the fence diagram, which we have done. So there are 5 boreholes. Based on this, the stratification was done as 5 layers, and also based on the one-dimensional resistivity data. And next, we have discretized this into triangle, 6 nodal prisms by using the triangulation technique. And the top elevation of the model was given by SRTM DEM. We have also used SRTM DEM 90 meters Cartosat, but we found that SRTM DEM, when compared with the ground control points, SRTM DEM of 30 meters spatial resolution had a good correlation with the ground points. So we have taken SRTM DEM data, 30 meters spatial resolution, and the bottom of the aquifer was decided based on the topography which we know. So 40 meters below mean sea level was taken. This is about the discretization. And coming to the boundary condition, so the coastal region, we have given equivalent head, where the equivalent head is calculated from the known density of seawater and the freshwater. And the datum is considered to be 40, and we know the density of seawater as well as fresh water based on that. And we have considered the concentration to be 35 kg per meter cube, the TDS value as. And the other boundary condition, okay, next is the other boundary condition is known from the observation wells. From the observation wells, we know the water level, and we have given the interpolated the data for this particular region and varying head boundary condition, which monthly is given to this boundary condition. And here at the top, it's the river. So river is, as we know that there is an interaction between the groundwater as well as the surface water. So cautious boundary condition should be given where there can be inflow, that is from the river to the groundwater, or groundwater outflow from groundwater to the river. So cautious boundary condition should be given. So to give this cautious boundary condition, the input which we have to know is what is the head in the river from the data, and what the material of the bed, the K value of the bed material, riverbed material, and what is the thickness of this bed material. So this can be given as input to the model. And next is about the initial conditions. As I've told, there are 14 observation wells, and at these observation wells, you can see that we have discretized finely conductivity for the initial month. So similarly for the solute concentration we have done. So the initial aquifer parameters, which we have from the pumping test, and also we know that the depth of the pumping test, it was done in the shallow wells. So we have limited that to first layer. So the pumping test data will give you only for first layer. So we have interpolated by kriging, and you can see the heterogeneity of specific yield in first layer. In case of layer 2, we know the geological formation from the ERT profiles. So we have given the ranges which is taken from groundwater estimation committee. So similarly for the hydraulic conductivity, as it is limited to the first layer, we have given the K value for the first layer, you can see, and found the heterogeneity part. As we were not aware of it, the KYY and KXX, we have in the other layers, we have considered a homogeneous KXX and KYY. And for the transport parameters, we have used porosity from the reference again, and longitudinal dispersivity, we have again used an equation to estimate the longitudinal dispersivity based on the observation the length. So we can estimate it based on the known length from the concentration. This L is the length from the concentration to what extent the contaminant can be transported. So the traverse dispersivity is also taken from the literature. So in that area, there are around 374 wells. This data was taken from the pumping rates, and number of wells were taken from the literature. And also based on the rainfall data, we have estimated the recharge, and this density is, we know that it is considered to be, the freshwater density can be considered as 1000 kg per meter cube, and for seawater it can be considered as 1025 kg per meter cube. And these are the other for the transport modeling. So now this is the initial model development. Now we have to do inverse modeling to estimate the parameters. So we know the H value for various time scale, and now from that we have to estimate the K values. For that inverse modeling, where best runs the free flow model, which we have used for the forward modeling iteratively based based on Gauss-Liebenberg-Marquardt algorithm to minimize the H. So since I have used this concentration also, concentration is also minimized, the concentration value. So when you run forward modeling, considering it to be homogeneous and isotropic, so you get some H value as a result, the simulated value. And this is the observed. And you try to minimize this error. So this is the objective function iteratively by changing it. So that is how you do it by changing iteratively, by minimizing this error. So the constraint you have to, so if you don't give the constraint, the values of K can range up to 1,000 meter per day. So you can, you know the region. So you give an upper limit as well as a lower limit and constrain the equation so that the K values will not go beyond the values which you are aware of. And also you can give the termination criteria where you want to, what are the reasons at which this minimization iteration should be stopped. So when the objective function is less than, or the error is less than or equal to 0.25, and if the iteration is more than 30, and also if the first, what happens after some point, there is no reduction in the objective function from the previous trial. So then you can terminate, as well as if the parameter values are not changing from the previous iteration, then you can terminate the criteria. These are the criteria given to this PEST model. This is the inverse code. And now since we have applied, how we have made few pilot points. We will be doing this inverse modeling only at these pilot points, and the rest will be interpolated by Kriging. So these pilot points have been spaced randomly. So, and this is spaced in all the layers. We want to estimate the hydraulic conductivity, heterogeneous hydraulic conductivity in all the layers, as well as in KXX and KYY. So totally we are estimating 225 parameters. So in each iteration, 225 parameters will be estimated. So there are 15 in each layer. So 5 layers for KXX, 15 and 5 layers, 15 point in each layers and 5 layers. So in KYY, totally we will be estimating 225 parameters, which also includes the longitudinal dispersivity. Also, we are estimating that is a transport parameter. So in the inverse code, we have used the concentration term also. So this is the results. The computational time taken was too much, that is 1,620 hours. So we had used normal computer. We can also go for high performance computers, but we used this as we had used for doing the geostatistical technique. We had used the normal computers, so we didn't go for high performance computers. So in each layer, you can see that the variation of K in XX as well as the YY. This is the box plot where it will give you the mean, and geometrical mean is indicated here. And you can see what is the least and up to what point it is extending in each layer. Similarly, in while it is shown in this. So this is the spatial heterogeneity that was in box plot, and here I've shown in this spatially. So this is for KXX in all the layer and KYY. So this is how we have estimated the hydraulic conductivity in X and Y direction. Now, what's the importance of considering anisotropy or heterogeneity is the question. So, what we have done is we have estimated the flow by using homogeneous isotropic model as well as from the results obtained from inverse model as well as from scale model. But in upscaling, we have used only one iteration, that is one realization. So in geostatistics, we can have random number of realizations and run the numerical model. But we restricted ourselves to one realization and we observed the one realization result. We compared the one realization result of the upscaled model, which is in black, with the inverse model result and basic model that is considering homogeneity as an isotropic way. So from this result, it was clear that inverse model was performing better compared to upscale model as well as the basic model. In case of upscale model, we had only used one realization. So that may be the reason. So, but the computational time or the computationally efficient computers are required for the inverse modeling. So that was the main disadvantage of inverse model. So conclusion of this overall parameter estimation is, so we have proposed a methodology where we can use one-dimensional resistivity data with the two-dimensional resistivity data, characterize the aquifer in three directions. So anisotropic hydraulic conductivity can be estimated. So this method which we have proposed to estimate in three-dimensional is simple, and also the resistivity data is cost effective compared to the conventional pumping test. So, and also coming to the geostatistic thing, not many researchers have concentrated on upscaling the K value in anisotropically. This was a main highlight of this geostatistical method which we have proposed. And in inverse modeling, again, uh, not many have considered the anisotropic as well as layering when they're doing the inverse modeling. So most of the models, when they do the groundwater flow modeling, they calibrate. But what they one of the limitation of those studies are either they consider steady state model, or next limitation is they consider the hydraulic conductivity to be homogeneous. So for this particular study area, we have found that we did the sensitivity analysis and we found out that hydraulic conductivity and longitudinal dispersivity are the two sensitive parameters for the groundwater flow and solute transfer. So we have concentrated only on hydraulic conductivity. So in inverse model, it gave a better result, but it is computationally demanding. So this is about, these are the few references which I've used, and I conclude. Thank you.
Thank you, Priyanka. Thank you for sharing your valuable time in spite of your busy schedule. Participants, if you have any queries, you can unmute yourself and you can clarify, or you can post it in the Google Meet messages.
Sorry, I'm not able to hear. Hope others are. I'm not able to hear you properly. Your voice is on and off. It's not clear.
Now, am I audible, Priyanka?
Sorry.
Yeah, dear participants, any queries, please post it in the Google Meet, or you can directly unmute yourself and you can clarify your doubts. Any queries, participants? Yeah, I think no queries.
Madam,
Hello, sir.
Madam, I saw that you have used the data of coastal data of 2008 or 9 like that. You have made some modeling analysis and all. Have you validated your modeling?
Yes, sir. I have validated the results. So now for the case estimation, sorry, I think I missed. So to estimate the K values, what we have done is for the inverse modeling results, which we have estimated. So I'll show you the results also, so it will be clear. We have estimated from the ERT profiles itself. Sir. So we know the from the first topic where we have estimated the where we have built a relationship between the resistivity and K. So with that profiles, the inverse modeling results which we got, K values were validated. Give me a minute, sir. I'll show you the validation also. Can you see this, sir?
Yes, madam. Yes, yes.
This is the ERT image,
Yes.
and this is the inverse modeling output. So this is the information which we have, the result which we have got compared. This
Right,
is
right.
valid.
Okay. Okay, madam. Thank you very much. Thank you.
Thank you, sir.
Thank you.
And there is one more query.
Yes, sir.
Can you correlate the electrical resistance that is obtained to
Sorry,
the
sir, your voice is not clear.
electrical resistivity
Yes, sir. Electrical resistivity.
that is obtained?
Sorry, sorry, sir. I am. Your voice is not clear, so I heard only electrical resistivity.
Am I
Am I
audible now?
audible now?
Yes, sir, you are audible.
So
Okay.
the
So the electrical
electrical
resistivity
that
that
you are
you are going to use
can be
can be
correlated with the
correlated with the bedrocks also.
Oh, yes, definitely. That is what it is for. See, the resistivity profile, it is for bedrocks also. If you have the data, you can estimate. I have shown you. So up to 1,000, I'll show you the. Okay. So we have taken the resistivity. So can you see?
yes, madam.
Yes, madam. Yes.
So in this, so the bedrock, the resistivity values up to 1,000 ohm meter has been used. Beyond that, we have not used. Sir. So only up to 1,000 meters. So we can, uh, or the consolidated formation can be considered from 650. The resistivity profile, if the resistivity value is more than 800 plus we can consider it to be a unconsolidated formation. Up to 1000 ohm meter, we can estimate the K values.
Okay, what
What
software
software exactly
is
it
used
is
here,
being
madam?
used here, madam?
So this the resistivity profiles was done by the other researchers. So they have used RES 2D to inverse this resistivity data, which they have got in the field. So analyzing the data was my part. So they have done this resistivity test and given me the ERT profile. So the ERT profile data was given to me where I am using it to estimate the K values. So they are using RES 2D to get the inverse of to do inverse modeling for the electrical resistivity data.
Thank you, madam.
Thank you, madam.
Yes, sir. Yes, sir. Yes, sir. Yes. Dear
Dear
participants,
participants,
please,
any queries? Madam is there to answer.
if there is any
If there is any queries, you can unmute yourself and
ask the
ask
questions.
the questions.
Yes, there is
There is one more query, madam.
Yes, sir.
What all the parameters used for the groundwater modeling of the area?
Sir, there can be porosity, specific yield, and that is longitudinal dispersivity, traverse dispersivity. All these parameters can be should be given. I've also showed in the presentation where what are the input parameters and specific yield, as I was concentrating on the unconfined aquifer. So I've given the specific yield, hydraulic conductivity, and porosity, longitudinal dispersivity, traverse dispersivity, and these are the. And also, you can give fresh water density as the input. And if you're doing the solute transport, the molecular diffusion values, viscosity of fluid can be given, sir. And also the density of these solutes if you're doing the solute transport.
There is one more query.
Yes, yes.
How do we calculate groundwater flow gradient?
Groundwater
Flow gradient.
groundwater flow gradient is nothing but, see, what you do is there are two wells. So the wells which is flowing, that can be estimated. So I don't have a figure to explain it. And okay. I'll send you one paper or not paper, this thing how to calculate it, because if I write and explain it will be more clear than me explaining orally.
Okay.
Is it fine?
Yes, yes. Yes. There is
There is one more query, madam.
Yes, sir.
Will the
Will the
groundwater
groundwater flow be unidirectional or
multidirectional?
multidirectional?
When it
When
is
it is
unidirectional,
unidirectional,
then what will
then
be
what
the
will be the
velocity that is
velocity
being
that is
obtained?
being obtained?
Is it
So the
Is it
dependent on
velocity
dependent
the
on the
flow is really less. So when we are doing this potential, when we have estimated the, when I say hydraulic head, so in this hydraulic head, we will be concentrating only on potential head and the datum head. The velocity head is neglected. So the velocity in the groundwater is very negligible. And also, as I'm telling, it is three-dimensional. It is a three-dimensional flow, sir. Very less. So I have not estimated the velocity. So it, as we say, it can be Darcy velocity. It's called as Darcy velocity. So there it is very negligible, sir. The velocity in groundwater flow is very less. But you can also, the Darcy velocity can be estimated, but I have not estimated, but it is very less, sir. And it is three-dimensional.
Thank you. And
And I think there is no more queries.
is there any queries? Is there
Is there any queries? Yes.
Dear
Dear
participants,
participants,
Madam is
madam
online.
is online. You can ask directly.
Unmute
Unmute
yourself.
yourself and you can
Go ahead with
go
your
ahead with your questions.
There is no more
There's no more
queries.
queries.
So
Uh,
thank you, madam.
Thank you for a
Wonderful
wonderful
session.
session.
It was a very
It was a very
interactive
interactive
session,
session,
and I think
and I think
hope the
hope the
participants have
participants
a
have
lot of
got a lot
insight
of insight
on the
on the
groundwater
groundwater
hydrology.
hydrology.
On behalf
On
of
behalf
JNN
of
College of
JNN College of
Engineering
Engineering
and
and
Hydro-Geological
Hydro-Geological
Engineering
Engineering
Workshop
Workshop Team,
Team, I extend
I
a hearty
extend a hearty
welcome
welcome for you, madam.
and a
And
very
a very
hearty thanks
hearty thanks
for such a
for
wonderful
such a
session,
wonderful session
for
today,
sparing
for
your
sparing your
valuable time.
valuable time with us.
Thank you very much.
Thank you very much.
Thank you, sir. Thank you all.
So the
The Google form has been shared. All of you, please do
give the
give the
feedback
feedback
for today's
for
session.
today's session.